EMBA 735 instructional video prepared by Professor Ahmed Tara, School of Management, George Mason University. In this video clip, we'll go through a demonstration of the process start to finish of building a causal loop diagram of my mental model of the system structure underlying the behavior implied by Brooks' law. So in an earlier slide we had mentioned Brooks' law, we had talked about it, and in brief, Brooks' law says that adding manpower to a late software project makes it later. And in that slide I had expressed to you my mental model underlying this observed phenomenon in narrative form using natural language. We will demonstrate now the process of converting that mental model that I have in an abstraction in my mind as a causal loop diagram. So let's begin by observing that a causal loop diagram, its basic constructs consist of variables and causal links. These variables are properties of the system, including components that interact with one another, characteristics of the system, and so forth. Okay. Now, how many variables should you have? Which variables are relevant? Which variables are not relevant? What is the appropriate level of abstraction? These are aspects of developing the causal loop diagram that you will develop a feel for over time with experience. Okay. So one of the things, though, we can say for sure is that since the central tenet of systems thinking is structure causes behavior, using our iceberg metaphor, if I'm trying to explain the behavior noted by Brooks' law, that is adding manpower to a late software project makes it later, if I'm trying to explain that behavior based on an underlying system structure, then of course there has to be at least one variable in the system structure that captures that observed behavior. Otherwise, I have no hope of linking the structure to behavior. So let me start by putting in a variable somewhere on the screen that reflects the observed behavior. So since Brooks' law deals with the lateness of software projects, adding manpower to a late software project makes it later, I choose to represent a variable called lateness. This is a property of the underlying structure, the system, and there will be a network of cause-effect relationships that will impact lateness, and that will be the basis for my linking structure to behavior. So I begin with this variable called lateness, and then I try to work around it. What effects? So if this is the effect, if the effect of the system is lateness, that's the behavior that I'm trying to explain. What affects lateness? Now, in my mind, lateness is the difference between the delivery date for the project and the forecasted completion date. If the forecasted completion date is after the delivery deadline, then of course I have lateness. So this tells me that I should have probably at least two other variables related to the system in this structure. One would be the delivery date, and the other is the forecasted completion date for the project. Okay. Notice that I could be wrong, and maybe these variables will turn out to be not so relevant. The way that causal loop diagrams evolve, the structure will give you hints as to whether you're headed in the right direction or there are logical contradictions in your reasoning. That's sort of part of the beauty of causal loop diagrams. Another thing that I would another piece of advice that I would give is humans are very poor at reasoning with chains of sequences of cause-effect relationships. They're very good at deciphering local effects, but global effects deducing in your mind is fairly difficult to do. So we'll start off from this variable called lateness and build on it in steps, very gradually, locally, as it were. So lateness is determined by the delivery deadline and the forecasted completion date. So let me put those two variables in. So I will say delivery deadline. By the way, I'm using the Vensim software to draw this causal loop diagram. You can draw it with paper and pencil also, of course, if you like. There's a separate YouTube video that I have developed showing you how to use the Vensim software for drawing these diagrams. Okay, so delivery deadline is a variable, and let me put in the other one that I mentioned, and that's forecasted completion date. By the way, this may not be a very good name. Should be compact. Having very long names, while they're very descriptive, they take up a lot of real estate in the picture. So there's a conflict there. You want a very descriptive name, at the same time you don't want to take up too much real estate. Okay. Now that I have three variables which are part of the structure in my mind underlying the behavior of Brooks' law, I will try to connect them. Notice I'm not trying to identify all the variables right at the beginning, and they will evolve. So I have three variables here. Let me first capture the relationship among these three that's there in my mind. And so forecasted completion date affects lateness. So I took my causal link. I started at forecasted completion date and ended up at lateness. So there is the cause and there is the effect. And let me bow it out a little bit so it looks nice. Straight arrows don't look so nice. Curved arrows tend to look better on causal loop diagrams. So forecasted completion date and lateness. Now remember what we said about determining the polarity of links. When you're determining the polarity of links, think about the link in isolation. So if I want to determine whether this causal link is positive or negative, I will not care about delivery deadline. There are all kinds of other things that affect lateness. So here I'm only concerned about the relationship between forecasted completion date and lateness. So I think you will agree that everything else remaining fixed, if the forecasted completion date increases, in other words, the date increases, then lateness increases. So Brooks' law said that adding manpower to a late software project makes it later. The project is already late and we are trying to add more people. So if the forecasted completion date were to increase, then lateness would increase. Okay, so cause and effect move in the same direction. So this link would have a positive polarity. Okay, so notice I paid absolutely no attention to the other input to lateness, delivery deadline, while I was determining the polarity of this link. So now let me connect delivery deadline to lateness, and I can say that everything else remaining constant, if the delivery deadline were to increase, for instance, I now have to deliver the project on September the 15th instead of March the 15th, then of course my lateness would drop. I get more slack. So I'm given more time. So everything else remaining constant, lateness would drop. In other words, delivery deadline, the cause, and lateness, the effect, their changes move in opposite directions. So I would put a negative polarity on this link. Very well. Now I have at least a piece of the structure in my mind that I've put down in terms of cause-effect relationships. So what does lateness do? So since we are late, we hire new workers. Okay, that's what Brooks' law effects in fact refers to. Adding manpower to a late software project makes it later. So at least let's add a variable in my mind that captures the fact that we are hiring new workers. So I will add a variable called workers. Okay, now you may or may not put this next variable that I'm thinking in my mind. I want to keep an inventory of the total number of workers that I have on staff, because after all, the total number of workers that I have will affect the rate at which work gets completed, and hence the forecasted completion date and so forth. So I would like to put in another variable called, at least at this point in time, I think it will be a useful addition to my structure. Okay. All right. Now that we have a couple more variables, I want to think about the relationships that might exist among these two new variables that I have added, and with the three previous ones. Okay. So by my thinking, again, I'm trying to articulate my mental model of the structure underlying Brooks' law. If I'm late, then I hire new workers. So I would like to show a cause-effect relationship from lateness to new workers, and the polarity of that link should be positive, because if the lateness increases, I would like to add more new workers. So by that logic, the cause and effect, the changes move in the same direction. So this link has a positive polarity. Now if I add new workers, that's the cause. The effect of that is to increase the total number of workers. So I would like to add a causal link, a link from new workers to total number of workers, and I think you would agree that this link would have to have a positive polarity. Okay. Notice when I put this positive polarity from new workers to total number of workers, I did not take into consideration any other links that might be coming into new workers or any other links that might have been coming out of total number of workers. I focused only on the cause and the effect, new workers, total number of workers, and the relationship between them. So now what happens if a total number of workers goes up? Now, by my thinking, if the total number of workers goes up, the rate at which work gets completed goes up, and hence the forecasted completion date should go down. Okay, so I'm trying to get my project back on schedule. So increasing the total number of workers increases the rate at which work gets completed. So in my mind, I would like to add an intermediate variable just to be explicit in representing my thinking. So I just write work completion rate. Okay, so that's my thinking, and my logic is as follows. If total number of workers increases, the rate at which work gets completed also increases. Okay, so this link has a positive polarity. Again, notice that each time I'm drawing the polarity of a link, I'm considering that link in isolation. I'm not trying to reason through any chain or loop. Okay. So now when I see this particular structure, it immediately occurs to me that work completion rate will have an impact on the forecasted completion date. If work completion rate goes up, forecasted completion date should go down. The project should be completed sooner. Similarly, if work completion rate were to go down, the forecasted completion date should increase. The project should be delayed. So the changes in the cause and the effect here, they move in opposite direction. So when I draw a causal link from work completion rate to forecasted, that would be a negative link. Now, as soon as I have this little structure, it occurs to me, as what is visible right over here is I have a feedback loop. So I go from forecasted completion date to lateness, or rather, let me start from lateness. I have a negative feedback loop here. Why? I start from lateness, I go to new workers, total number of workers, work completion rate, forecasted completion date, back to lateness. So that's a feedback loop. So is that a positive or a negative feedback loop? You take the polarities of the links on that loop, multiply them, and I get a minus. So I have plus times plus times plus times plus times minus. Okay, so 4 pluses and 1 minus in that loop. When I multiply the 4 pluses and 1 minus, I get a minus. That's a negative feedback loop. Meaning what? That if lateness were to increase, the system reacts in such a way to reduce lateness. That's what I would expect in terms of the logic, that adding new workers increases the total number of hours spent on the project and therefore increases the work rate. So this negative feedback loop that you see here is the logic that would have explained the green dotted line that I had referred to in the Brooks law behavior picture that we had discussed earlier. But Brooks law says that that is not what happened. The project does not get back on schedule. Rather, adding manpower to a late software project makes it later. So something else, some other forces must be at work. And you remember in my narrative, I had said that adding new workers increases overhead, both communication overhead and training overhead, and that has reduces the average productivity and negates the effect of this increased number of hours spent on the project. So by that narrative, there are at least 2 other variables in this structure that I need to represent. One is training overhead. So you remember that phrase in the narrative, written narrative. So you could measure training overhead in terms of the number of hours spent training the newbies. Okay, and let me also put the second variable, which is communication overhead. Okay, so now that I have these 2 additional variables, I will enhance this structure further by trying to capture what I think are the causal relationships that exist among these new variables that have been introduced and the existing structure that's there. Clearly, one cause-effect relationship that exists is between new workers and training overhead. Okay, so when you bring new workers on board, there's training overhead. And what would be the polarity of that link? Clearly, it has to be positive, because the more new workers I have, the more training overhead I incur. Okay, so the cause and effect, the changes move in the same direction. The less new workers I have, the less training overhead I would have. Okay, so there the link is positive. Okay, now let me move this a little bit to visually get some space. Okay, similarly, if I have new workers, there's communication overhead. So I have a cause-effect relationship from new workers to communication overhead, and by a similar reasoning as that of training overhead, this link polarity would be positive. Again, notice that as I'm determining the polarity of this one link, I'm not bothered about all the other chains of cause-effect relationship that are there in this diagram, in this causal loop diagram. Okay. All right, so I have training overhead and communication overhead, and clearly that somehow affects the project. And if you remember from the narrative, what we said is that these overheads, they reduce average productivity of the workers, both the new and the existing workers. So this suggests to me that I probably ought to have a variable in this structure called average productivity. Okay. Once I have this variable, again, I would try to build up the causal relationships here. What this tells me is there is a relationship from communication overhead to average productivity. And I think you can guess what the polarity of that link would be. That would be a negative polarity. Why? Because the cause is communication overhead, the effect is average productivity. As communication overhead increases, average productivity decreases, so it's a negative link. So by the same logic, you would have a negative link, causal link, connecting training overhead to average productivity. So here I would put a negative link. So now, what does average productivity, what impact does it have on the project? Obviously, it affects the work completion rate. Okay, so I draw a link from average productivity to work completion rate, and I want to determine the polarity of this link. In doing so, I'm going to completely ignore the two inbound links into average productivity. I'm going to completely ignore the outbound link from work completion rate to forecasted completion date. Okay, I'm going to concentrate only on this one link from average productivity to work completion rate, and ask myself, if average productivity were to increase, would work completion rate be higher or lower than it otherwise would have been? Obviously, it would be higher. So by that logic that we had discussed in a previous slide, this link polarity should be positive. Now, you can refine the structure much more if you like. So in the interest of time, I will stop in terms of the level of detail. But notice what has just happened. I have been drawing this picture one link at a time, but some additional circles of causality have arisen. So previously, we had this one feedback loop from forecasted completion date to lateness, new workers, total number of workers, work completion rate, forecasted completion date. And our reasoning told us that this was a balancing or a negative feedback loop, meaning if lateness increases by adding new workers, I'm increasing the total number of hours spent on the project, and that should get the project back on track. The forecasted completion date should shrink and lateness should go down. However, there are unintended side effects. Now, if you look at two additional feedback loops that have just arisen because of the enhancement to the structure, let's start from lateness again. Lateness, new workers, communication overhead, average productivity, work completion rate, forecasted completion date, back to lateness. So that's another feedback loop. So is that a positive or a negative feedback loop? Let's look at the link polarities. Plus, plus, minus, plus, minus, plus. So if you multiply those polarities together, I think you have 1, 2, 3, 4 pluses and 2 minuses. If you multiply those all together, you get a plus, which means this is a reinforcing or a positive feedback loop. This is very alarming because look at what it tells you. It tells you that if lateness were to increase, and you add new workers. The system reacts by adding new workers, but the effect of this feedback loop is such that it goes ahead and increases lateness even further because average productivity has been reduced. So if you look at this overall structure, you have a balancing loop, a negative feedback loop resulting from adding new workers that is trying to reduce lateness. On the other hand, you have two positive feedback loops that is trying to further increase lateness because of the reduction in average productivity. So this is my causal loop diagram representation of the structure underlying Brooks' law, and I've just tried to link this structure to system behavior for you. And now, as soon as you see a CLD like this, it lays bare my thinking in all its shortcomings, but it's a very precise representation, and you can use this to further to question my thinking and to perhaps refine it and make this model much more accurate. Compare that to a narrative in text form. A text narrative is linear. It's fairly difficult to figure out feedback loops and circles of causality from a textual narrative description of an underlying structure. So this is the process of constructing a causal loop diagram from start to finish.